Hello everyone. In this video we are going to see the proof for lower bound for element distinctness problem under the course Design and Analysis of Algorithms by Professor Sharma Tankachan, myself Vikram Rajiv Reddy. So let's get started. So we'll see what is element distinctness. So we have for a sequence of numbers, let's say x, where x1, x2, n3 and x1, xn, we should print yes if all the numbers are distinct and no if there is similar numbers exist in the sequence. So let's take an example here. So where is x is 1, 2, 3, we have yes, and x equal to 1, 1, 3, we say no. So this can be easily computed by comparison and sorting in we go nLogn. However, we are seeing the proof for the lower bound, which is omega of n log n. That is, we cannot make it tighter than n log n. So for that, first we'll see the lower bound for the sorting algorithm, which can be computed in omega of n log n, and we'll see the proof by the decision tree method. Now we can see. So yeah. So let's take a1 is equal to 1, a2 is equal to 2, and a3 is equal to 3. In the decision tree method, we have the root like where we are first comparing a1 with a2, which is 1 and 2. If 1 is less than 2, it is yes. And now let's check 2 and 3, and we get this. One of the sequences 1, 2, 3, and similarly we have 6 outputs for a sequence of 3 numbers. So which is 3 factorial is 6 outcomes, which is n factorial. So the lower bound for a sorting algorithm is tree height is of n factorial, which can be computed to be omega of n log n. Yeah. So we have seen the lower bound for a sorting algorithm. So we take this as a reference for proving the lower bound for element distinctness. Based on the previous algorithm which we have seen, we can compute the lower bound for element distinctness based on the sorting algorithm. For that, they have n factorial outcomes. Now for the lower bound for element distinctness, we have only 2 outcomes, either yes or no. So let's say it is log 2, which is equivalent to 1, which is not useful. So we cannot prove it the way we have proved the lower bound for a sorting algorithm. Yeah. Here we need a different approach to find the lower bound for element distinctness. So let us look at the claim. So let x is x1, x2 and x1, xn, which are distinct elements, and y, which is a permutation of x, which is y1, y2 and y3 and so on. So So for us to pull lower bound for an element distinctness problem, let us take x is x1, x2 and so on xn, which are distinct elements, and y is the permutation of x, which is y1, y2, so on. And so for us to prove at least there are n factorial leaves of s, each permutation of x should reach a different path to s. So that is a distinct path. So if we can prove that there are n factorial s path, then we can say at least we can prove the lower bound like omega of nLogn. To prove that, we take, so let us assume for x and per y, which is permutation of x, one of the permutation of x, they reach s path with the same path L. So let us take z, which is z1 to n, and z1 to zn in n coordinates, like lambda xi plus 1 minus lambda of yi, which is some weights of xi and yi. Yeah. So we keep this aside. And to prove the lower bound for element distinctness, we also have a subclaim. There exists ij such that xi less than ij and yi greater than yj. So let's see an example here. Let's say we have 1, 2, 3 as x, whereas y is 3, 1, 2. Xi, let us take I is equal to 0, j is 2. So in this case, xi is less than ij, so 1 is less than 3. Here, xi 3 greater than 2. So we have claimed this, and we have claimed that every permutation has taken the same path L. So let us assume that x is on path and y. So let us assume that z is also is on the path of x and y. And now here we are proving that when x is belong to the same path and y also belong to the same path L, if z is also on the same path, there exists similar, there is no distinctness in the elements. We are proving that answer of z is no. So there is a little claim here. So let us assume we have a function f of w, which is the difference between the two coordinates wy and wj. So let us assume this. We have the subclaim like xi less than xt and yi greater than jj. So now with this, f of x is less than 0, we take f of y, is greater than, it's greater than 0. We have a mean value theorem which suggests that when z belongs to the same path p such that where z belongs to the same path p such that f of z is 0. So if f of z is 0, which implies zi minus zj equal to 0 and zi equal to zj, which means there is no distinctness in the Z elements. So which is Z is also lying on the path of X and Y. So we can say that X has taken a path L1, let's suppose, and the permutation of X, which is Y, has taken an L2 path, and so on. There will be n factorial permutations for X, and similarly we can say that when the tree height is equal to O n factorial, which is omega of n log n. Thank you.